All right, so tonight for homework, you should be working on this review packet. We're going to start by looking at some sequence information. And sequences are really just looking at equations, right, and patterns in the equations. But something you need to know is a recursive sequence is a sequence that refers to the term before it, and you need to use that term to find the next term. So it must also give you the first term. So a function k whose domain is the set of positive integers, okay, which means the inputs are only positive integers, as k of 1 equals 4. And k of n equals k of n minus 1 minus 2. So it's asking you if we were to input k of 1, we would get 4, right? So then it's saying k of n minus 1 is looking at the term before it, and then subtracting 2 gives you the next term, right? So if we were to look, for example, at k of 2, then that would be k of 1 minus 2. So k of 2, for example, would be k of 2 minus 1 minus 2, or that means k of 2 equals k of 1 minus 2. We know k of 1 is 4. That means that this k of 2 equals 4 minus 2, or 2. So we know that this one right here is definitely true. And so that means that as the sequence is moving along, it's going down by 2, right? So we can also reason that the sequence before that would be, right, if we did the sequence after that, if we did k of 3, for example, would be 0, because we are decreasing by 2 each time. Since we're decreasing, we can eliminate k of 6 equals 3, and then k of 0 equals negative 2. So here the thing about this one, it says k of x whose domain is a set of positive integers. So 0 is not a positive integer, and negative 1 is not a positive integer, so these also are not going to work out. If we were to look at k of 6, that would be the 6th term in the sequence. So we're doing 4, 2, 0, negative 2, negative 4, right? We would not get 3. 1, 2, 3, 4, 5, 6 would be negative 6. So that is not true, okay? So again, this is just saying the term before minus 2 gives us our next term, which means we are decreasing each time by 2. All right, arithmetic sequences are sequences that are linear sequences. So these are linear equations. It's just another word for what is a linear equation. And this gives you this is on the Park reference sheet. This tells you how to find that equation. So if we write a function for this situation, we can write this as thinking about what is increasing by each time, because we're adding the same amount each time. So in this case, we're adding 65 each time. So our equation is going to be, let's say, for example, f of x equals 65x. And then we need to think about our starting amount, right? So 65x 110 minus 65 gives us 45. So plus 45. All right, and that's the function for that situation. You could also use this information to fill this out. So a of n, a of 1, right, f of x equals. So a of 1 is 110 plus n minus 1 times d. So where d is the difference between each term. So we could also write this as 110 plus 65 times x minus 1. And if you were to multiply that through, we would get 110 plus 65x minus 65, which is the same as this. So if you get stuck, you can also look at your reference sheet and you'll see this formula that can help you to work through that. All right, but remember, we're looking at the initial value plus the rate of change. All right, a geometric sequence is essentially an exponential function, right? So these are exponential functions in which we are multiplying by something. Here it says the starting amount was 2 grams. Write an equation that represents this situation. So f of x equals 2, our starting amount, times, then we need the factor. So that's what we're multiplying by each time. So 1.68 divided by 1.83 gives me 0.91. Let's try another one. 1.54 divided by 1.68 gives me 0.916. 1.4, oops, 1 divided by 1.54, 0.915. So approximately 0.92, we'll say. Yeah, that looks about right. Or if you wanted to 0.915, if you wanted to be a little bit more exact, to the power of x. All right, so you could also look at this as f of x equals the first term, 1.83, right? In this case, we're not multiplying by the original term, we're multiplying by the first term, times the rate, 0.92, to the power of x minus 1, which will actually get you the exact same thing if you were to calculate this, because this would be 1.83 times 0.92 to the power of x divided by 0.92. And so you will end up getting the same answer as you would up here, because 1.83 divided by 0.92 is going to give you approximately 2. Okay, so again, if you get stuck, you can use your CAPE reference sheet to use this formula, but if you just remember too that the original times the rate to the power of x is where we get our equation from, and that is an equivalent equation, so both are acceptable. All right, the second part asks calculate the average rate of change of grams from day 4 to 7. Remember, that's where we're doing y2 minus y1 over x sub 2 minus x sub 1. This is if we draw a line between those, what does the slope look like? So from day 4 to day 7, we have 1.09 minus 1.41 all over 7 minus 4, 3 days. And then we should get a negative term because it is decreasing. So minus 1.41 is negative 0.32 divided by 3, which is going to give us negative 0.1067. So it's losing approximately 0.1 grams per day. All right, population growth and decay. So this is the same as what we have been doing with exponential functions. It's just considering that if something is increasing and we have the percent increase, we write it as a decimal and add 1. If it is decreasing, we write the percent as a decimal and subtract from 1 to give us our factor, or the thing that we're multiplying by each time. It says write a function of the table above. Okay, so we have our starting point. The thing, this is going up by 2's, and that is not helpful for us. So if our starting height is 2, and then our factor is what we don't know, right? So we're going to have f of x equals 2 times something we don't know to the power of x. We do have this information, so I can plug that in. 3.38 equals 2 times 2 to the power of x. I'm going to divide by 2 first, so 3.38 divided by 2 gives me 1.69 equals 2 to the power of x. Oh, sorry, I did that backwards. X to the power of 2, right? Because we have this as our input there. So x to the power of 2, and then we take the square root of both sides, and we get x equals, you will hopefully recognize that 0.13 times 0.13, or 1.3 times 1.3 rather, is 1.69, because 13 times 13 is 169. So this is our growth factor, and so that means we can rewrite this equation as f of x equals 2 times 1.3 to the power of x. All right, we saw one like this last week as well. All right, if Max buys a car for $46,000, it is now depreciating by 15% per year. So if it's depreciating, that means what's left of that is 0.85. And then it says how much will the car be worth in 10 years. So our starting amount is 46,000 times our rate to the power of 10. You can go ahead and calculate that yourself. I'm expecting to see an answer here. If Stella invests $1,500 for an interest rate of 1.5% a month, how much will the account be worth in 1 year? All right, so that would be 1,500 times, my rate is 1.5%, but 1.5% is written as 0.015, and then I need to add a 1 to that, so 1.015. So after a year, that would be to 12 months. Within 10 years, though, I'm going to need to multiply that 12 times 10, so 120. And again, I want you to go ahead and calculate what would those actual amounts be. How much money will she have? So simple interest here is thinking about if we're just adding it based on the same amount every time. You get $10 every year, right? Something like that. That is, again, our linear function. Compound interest is the one that we're almost always going to be looking at. Simple interest is very rare. So compound interest is our exponential function. Okay, and that means that we are adding the principal, or the original amount, times the rate to the power of time. Okay, so it says which statement can be interpreted from the equation of an automobile cost, 28,000 times 0.73 to the power of t, where c of t represents the cost and t represents the time in years. So the equation is an exponential growth equation. No, because we are multiplying by a number between 0 and 1. So this is decay. It's decreasing. It's depreciating. The equation is neither exponential decay nor exponential growth. No, it is decay. $28,000 represents the initial cost of an automobile that appreciates. So this word right here, right, we see appreciates. That is not true. 28,000 represents the initial cost, that's true, that depreciates 27% or depreciates 73%. So what's left is 73%, right? That's what's remaining. And so that means that it's depreciating 27%. So this is correct and this is not correct. This is how much is remaining, not how much it's depreciating. All right. Linear growth versus exponential growth. So it says draw an example of linear, draw an example of an exponential function. You can do that yourself, right? You're just like, draw a little graph. What do they look like? Interpreting exponential functions. So a t-shirt company bought this is very similar to the one up above where we're just interpreting this. So a t-shirt company bought a new packaging and tracking system for $100,000. The formula is $100,000 times 1 minus that percent to the power of y. In the formula, what is the meaning of the term 1 minus 0.125? So is it the value of the system will be 0 in 12.5 years? No. The value of the system will decrease by 1250 each year? No. The value of a system will decrease by 12.5% each year? Yes. That is our rate, that 12.5, and then we're creating the factor by subtracting from 1. All right. The next piece is looking at one solution, infinite solutions, or no solution. And so if systems of equations have one solution, if they have different slopes and different y-intercepts, they'll have one solution. If they have the same slope and the same y-intercept, right, they're going to overlap, and so they have infinite solutions. And they have no solution if they run parallel to each other, which means they have the same slope but a different y-intercept. So draw an example of a system of equations that would have one solution. I basically just did that over here, so you go ahead and do that. And then draw an example of a system of equations that would have no solutions. Piecewise functions are functions that have different rules for different intervals. So this one is a practice for if tickets are $1 for children ages 1 and younger. So $1 for children ages where x is less than or equal to 1. $2 for children ages 2 to 6. So where x is greater than or equal to 2 and less than or equal to 6. And $5 for everyone ages 7 and up. Draw a graph that demonstrates this. So you go ahead and draw that graph. I'm not going to draw it for you. I want you to practice doing that for yourself, but you should have 3 chunks of lines based on those prices. So $1, $2, and $5.